In this lecture, I'm going to cover a specific type of regression called logistic regression. And so I'll start with an overview about what logistic regression actually means, go over the statistical assumptions for logistic regression, and then cover statistical and practical significance in the context of logistic regression. So let's start with that overview. So logistic regression in its most simple forms can be either a simple logistic regression or a multiple linear regression. Now, a simple linear regression simply means that you have values on a single predictor and values on a single outcome. But to be a logistic regression, the outcome needs to be dichotomous, which is another word for binary. So classically, if we think in the HR context, a dichotomous outcome might be turnover versus staying. So someone quitting versus staying in the organization, we might code that as a 1 and a 0, where 1 means leaving the organization or quitting, and 0 means staying in the organization. Now, multiple linear regression is also going to have a dichotomous outcome variable, except it's going to have 2 or more predictor variables used to predict that dichotomous outcome variable. So I'll start first in this lecture by focusing primarily on simple logistic regression, and then after that, I'll briefly describe how multiple linear regression differs, but they're largely the same. It's just the matter of adding additional predictor variables and introducing the concept of statistical control when we get to multiple linear regression. So something that we need to consider when we're talking about any type of logistic regression is the concept of odds. So you might have heard of odds before, you might be very familiar with odds, but let's define it in the context of logistic regression in the context of probability. So logistic regression can be used to determine the odds that a dichotomous event occurs given higher or lower values on one or more predictor variables. So odds essentially are calculated using the following equation. So it's the probability of an event occurring, p, relative to the probability of that event not occurring, 1 minus p. So p over 1 minus p gives you the odds. So an odds of 1 in this context can be interpreted as 1-to-1 odds, which is just really another way of saying that the probability of event occurring is equal to the probability of the event not occurring. Or in other words, we commonly say there's a 50-50 chance. And so that's when the odds is equal to 1. So let's start with an example of how we actually calculate the odds. So at a given level of job dissatisfaction, for example, the probability of quitting is, let's say, 0.75, which means that the odds of quitting are then 0.75 over 1 minus 0.75, which comes out to be 3, which can be interpreted as there are 3-to-1 odds. Now, conversely, the probability of not quitting is 0.25, which means that the odds of not quitting are 0.25 divided by 1 minus 0.25, which comes out to be 0.33. Now, you'll notice here that the odds of quitting is 3, and the odds of not quitting is 0.33. Now, if we take the natural log, which is represented as ln, so that's a logarithm to the base e, which is Euler's number, more on that in a second. So by taking the natural log of both odds, we can create symmetrical values, and this is called a logit transformation. And so a logit transformation of 3 would come out to be 1.10. And so that is the logit transformation for the quitting value. Now the logit transformation of 0.33, which is for the not quitting value, would be negative 1.10. So you can see how those two values are in fact symmetrical, 1.10 versus negative 1.10. And so that's one of the values of doing a logit transformation, which is really comes at the heart of doing a logistic regression. So let's walk a little bit deeper into the forest that is simple logistic regression. So when you're thinking about a simple logistic regression, remember it represents the bivariate linear relationship between a predictor variable and a dichotomous outcome variable that has undergone a logit transformation. And so as you'll see in the plot to the right here, that there are an x value, there's an x value and a y value. And notice how the y value, there's really only 2 levels here. So we have the lower level and the upper level here. And so this means that this is in fact a dichotomous variable. And so let's assume for the sake of explanation that the x variable or the predictor variable in this example is in fact continuous. And so you can start to see where higher levels of the x variable, the predictor variable, seem to imply that you're more likely to be in the upper level of that y variable, whereas lower levels of the x variable or predictor variable seem to imply that you're more likely to be in the lower level of that dichotomous outcome variable. Now, here I also provide an equation or formula for how you can actually calculate a regression model that is logistic. And so you'll notice at the far right hand of the equation, this should hopefully look pretty familiar. This is the same as what you would see for the regression or the equation for a line that you would see in a simple linear regression. And so b sub 0 means that this is the constant or the intercept value. And then b sub 1 refers to the slope or the regression coefficient, sometimes called the regression weight, and x refers to values or scores on that particular predictor variable. Now, when we go to the left, though, we start to see something that should also look familiar, but is going to be distinguishable from a simple linear regression model. And so here you'll see that the natural log of the probability over 1 minus the probability, which if you remember from the last slide refers to the odds, the natural log of that is essentially what we're computing here. And so that's where that logit transformation comes into play. And so you'll see that represented by logit p here. Now, in addition, we should also note that the logit p for the logit probability is actually equal to the log odds. So sometimes you'll hear this referred to as the logarithm of the odds, or just the log odds for short. So typically, we represent in a simple logistic regression, we represent the relationship not using a line, a straight line, but actually something that's nonlinear in nature in the sense that this is a sigmoidal S-shaped curve. And so this represents the probability of an event of each level or value of the predictor variable in relation to that dichotomous outcome, and specifically the logit transformation of that dichotomous outcome variable. Now, as I mentioned previously, it's important to notice that this is still a linear relationship between the predictor and the dichotomous outcome variable, because that dichotomous outcome variable has undergone this logit transformation. Now, in terms of calculating the probability, so understanding how this relates to the probability of, let's say, any one individual based on their scores on the predictor variable, and plugging that into the regression equation here and understanding what is the probability of them actually, let's say, leaving the organization if this outcome variable is in fact staying, or rather staying versus quitting, where quitting is represented by the value 1 and staying is represented by the value 0, thereby making a dichotomous variable. We can see that we can take our regression equation, as I just showed you before, and that's going to predict the natural log of our odds, which again, where the odds is calculated by the probability of an event occurring over 1 minus the probability of that event occurring. And so the next thing that we can do, in order, if we actually exponentiate out the natural log, we'll find that the log, or rather the odds, is equal to Euler's E, which is represented by that little e there, which let's make sure we distinguish that that doesn't refer to residual error or anything like that. This is in fact a mathematical concept, or constant rather. So Euler's E represents Euler's number, which is an irrational number, meaning it is not the ratio between two integers. And it's also a mathematical constant, much like the idea of pi in mathematics. Now, it's approximately equal to 2.71828 and so on. It goes on and on and on. And so it's important to remember that this is what E stands for in this context. It's Euler's number, okay? So if we exponentiate that, we take Euler's E to the value of the regression equation based on whatever value we plugged in for a particular individual, we can actually calculate, doing so, the probability of that individual having that higher score on that dichotomous outcome variable. And in, let's say, the example, it's the likelihood or the probability of someone actually quitting the organization. And so to calculate that, we would simply take the Euler's E to the result or of the regression equation after we've plugged in the x value for that particular person over or divided by 1 plus that same value. And that will give us the probability of that person having that high score on that dichotomous outcome variable. Okay? And so this is a way that you can then create individual predictions for people using logistic regression. Now, when you do a logistic regression, like simple and multiple linear regression models, you're going to get regression coefficients for your estimated model. And these are not going to be, however, easily interpreted in their own right, because the outcome variable has undergone that logarithmic transformation or that logit transformation. So rather, the regression coefficients represent the change in log odds for every 1 unit increase in the predictor variable. So to make the regression coefficient more interpretable, we often convert it to an odds ratio by exponentiating it. And so that's again taking Euler's E, or Euler's number, and then taking one of the regression coefficients, and so taking e to the power of that regression coefficient. And so in this notation here, b sub I represents the regression coefficient, which might be the intercept, the slope, weight, whatever you want to call it, or whatever you've chosen. And again, this e represents Euler's number, which represents that mathematical concept that's called Euler's number. So let's think about what an odds ratio actually means in terms of how to interpret it. So an odds ratio that is equal to 1 implies that there is no relationship between the predictor and outcome variables. In other words, there's a 50-50 chance. Now, an odds ratio that is greater than 1 implies that there is a positive relationship between the predictor and the outcome variable, meaning higher scores on that predictor variable mean it's more likely for someone to be classified into the higher level of that outcome variable that is dichotomous in nature. Now, an odds ratio that is less than 1 implies that there is a negative relationship between the predictor and the outcome variable. Now, it's also important to note that an odds ratio can range anywhere from 0 to positive infinity. Okay, so from 0 to positive infinity, and 1 implies that there's no relationship. So let's work through some examples of how to actually interpret an odds ratio and how to calculate it as well. So a simple logistic regression model, let's assume, includes the predictor variable of job dissatisfaction and the dichotomous outcome variable of voluntary turnover, where quitting is equal to 1 and not quitting is equal to 0 for that dichotomous outcome variable. Let's say that on our estimated model, the regression coefficient associated with job satisfaction is 1.010. Now, if we exponentiate 1.010, we get 2.746. And remember, by exponentiating, I mean taking Euler's number to the power of 1.010. Now, this is going to give us the odds ratio, okay, which is 2.746. So thus, the odds of quitting are 2.746 times as likely for every 1 unit increase in job dissatisfaction. So again, the odds of quitting are 2.746 times as likely for every 1 unit increase in job dissatisfaction. Let's look through another example here, which will illustrate another potential thing you should consider when interpreting an odds ratio, specifically an odds ratio that is between 1 and 2. So a simple logistic regression model is run, and this time the continuous predictor variable is age, and the dichotomous outcome variable is again voluntary turnover, where quit is coded as 1 and not quit is coded as 0. So let's assume that the estimated regression coefficient, which is the log odds, is 0.323. And if we exponentiate 0.323, we get 1.381, which is the odds ratio. So thus, the odds of quitting are 1.381 times as likely for every 1 unit increase in age. Or in other words, we can say it like it is 38.1% more likely for every 1 unit increase in age. So when your odds ratio is between 1 and 2, you can interpret it easily as a percentage in that regard, specifically as a percentage increase or percentage more likely to have occurred. Now, what happens when your odds ratio is less than 1? So let's assume now a different example and situation where we have a simple logistic regression model that includes the continuous predictor variable of employee engagement and the dichotomous outcome variable, again, of voluntary turnover, where quit is equal to 1 and not quit is equal to 0. So the regression coefficient we find from the estimated model is, let's say, negative 1.222. If we exponentiate negative 1.222, we get 0.295, and that 0.295 represents our odds ratio. And this value is less than 1. So how do we interpret this? Well, there's different ways that we can interpret it. So we could interpret it as being the odds of quitting being reduced by 70.5% for every 1 unit increase in engagement. So where did I get that 70.5% value? Well, if you take 1 minus the odds ratio, or in this case, which is 1 minus 0.295, we get 0.705. If you multiply that by 100, you get a percentage, which is 70.5%. Now, alternatively, if we take the reciprocal of this odds ratio, we get 3.390. And to review, a reciprocal simply means taking 1 divided by that value. So 1 divided by 0.295 equals 3.390, which can be interpreted as the odds of quitting being reduced by 1 in 3.390 for every 1 unit increase in engagement. Now, finally, you could also simply interpret the reciprocal as the odds of not quitting being 3.390 times as likely for every 1 unit increase in engagement. So we've just flipped the dichotomous variable there for interpretation purposes. So it is a little bit more tricky when it comes to interpreting those odds ratios that are less than 1, and it requires sometimes a little bit more math to get it into an interpretable fashion. So when we're talking about multiple logistic regression, because thus far we've been focusing mostly on simple logistic regression, multiple logistic regression again just implies that there are 2 or more predictor variables, but still that dichotomous outcome variable that undergoes that logit transformation. Now, because there are 2 or more predictor variables in the model, the concept of statistical control comes into play in this instance. And if you recall, statistical control is the idea that in the estimated model, we're providing the partial regression coefficients for each predictor while holding all other predictor variables in that model constant. In other words, you can think of this as being like looking at the net effect of one predictor while holding the others constant, or controlling statistically for the others. And so that's something we need to consider when it comes to the interpretation of those regression coefficients in a multiple logistic regression model where there are 2 or more predictor variables. So what are the statistical assumptions for a simple logistic regression model as well as a multiple logistic regression model? Well, fortunately, they're very similar. We just add on an additional assumption or consideration for that multiple logistic regression model. So starting with a simple logistic regression model, the assumptions are that 1, the cases, which in most of our interest is going to be employees in an organization, but that cases in your data set are randomly sampled from the underlying population. The second assumption is that the data are free of bivariate outliers. The third assumption is that the outcome variable is dichotomous, hence logistic regression. And then the fourth assumption is that the association between the predictor variable and the logit transformation of that outcome variable is linear. Now, what are the assumptions then of multiple logistic regression? Well, really, we're just adding on an additional assumption here. Now, the cases still need to be randomly sampled from the underlying population. The data need to be free of outliers, but in this case, specifically multivariate outliers, because we have 2 or more predictor variables. The outcome variable needs to be dichotomous, of course, and the association between the predictor variables and the logit transformation of the outcome variable need to be linear. Also, because we have more than one predictor variable, we need to be concerned about collinearity, which is sometimes called multicollinearity. And that is that we would prefer there be no multicollinearity, which means that there's no association or correlation between the predictor variables themselves. But a little bit is going to be okay. But if it gets too high, it's going to make it really hard to interpret the findings. And if we have perfect collinearity, it's going to make it challenging to actually estimate the model as well. So let's now talk about statistical significance in the context of logistic regression models. And we'll start with simple logistic regression. So let's assume that we're using null hypothesis significance testing and that our alpha value is set at 0.05 two-tailed. And so if our p-value is less than that alpha value of 0.05, then we would say that we've met the standard for statistical significance, meaning that we reject the null hypothesis that that regression coefficient is equal to 0. So this can be very similar interpretation to that of simple linear regression. Now, if the p-value associated with the regression coefficient is equal to or greater than the alpha level of 0.05, then we would fail to reject the null hypothesis that the regression coefficient is equal to 0. In other words, we conclude that that regression coefficient is not statistically significant. Now, in addition, we can also use confidence intervals, and if we set our alpha level two-tailed to 0.05, the equivalent confidence interval would be a 95% confidence interval. And so for a regression coefficient, if its 95% confidence interval does not include 0, then we can conclude that we met the standard for statistical significance. So now let's walk through an example of statistical significance in the context of simple logistic regression. So let's again assume a two-tailed alpha set to 0.05. And so if the p-value is less than 0.05, we conclude statistical significance. If it is equal to or greater than 0.05, we conclude that it is not statistically significant. So let's assume that the associated regression weight for the predictor value is negative 1.42, and the associated p-value is 0.01. 0.01 is less than 0.05, so we would conclude that that regression coefficient is statistically different from 0, meaning there is a significant effect here, and it is negative in terms of sign. Now let's look to the other example where we have another predictor variable, and this time that regression coefficient or weight is equal to 0.11. The p-value associated with it, however, is 0.06. 0.06 is greater than that alpha level of 0.05, so we would conclude that this is not statistically significantly different from 0 in this context. Now let's move on to statistical significance in the context of multiple logistic regression, which is when, again, we have two or more predictor variables in our model, but still that dichotomous outcome variable. So using null hypothesis significance testing, we would interpret a p-value that is less than 0.05 to meet the standard for statistical significance, meaning, in other words, that we reject the null hypothesis that that regression coefficient for that particular predictor variable is equal to 0. Importantly, while controlling statistically for other predictors in the model. And so this is again with multiple logistic regression, we're holding all other predictor variables constant when we're predicting a particular regression coefficient. You can think of it as being the partial regression coefficient after controlling for the effects of the other predictors in the model in relation to that same outcome variable. Now, if the p-value associated with the regression coefficient is equal to or greater than 0.05, then we would fail to reject the null hypothesis that that regression coefficient is equal to 0 while statistically controlling for other predictors in the model. So, in other words, we're essentially saying that that regression coefficient is not statistically significant, or in other words, the relationship between that predictor variable and the outcome is not statistically significant while controlling for other predictors in the model. Now, if we choose to use a confidence interval, again, the equivalent confidence interval for an alpha level of 0.05 that is two-tailed would be a 95% confidence interval. And so if that 95% confidence interval does not include 0, then we would conclude that we have met the standard for statistical significance. So let's walk through an example of statistical significance for a multiple logistic regression model. And again, we'll assume a two-tailed alpha of 0.05. So let's assume that the regression coefficient for a particular predictor variable is negative 1.42, and that p-value is 0.01. The p-value is less than our cutoff of 0.05, so therefore we would say the regression coefficient is statistically different from 0, controlling for the effects of other predictor variables in the model. And also note that the sign is negative here. Now let's move on to the second example for a particular predictor variable. Let's look at the associated regression coefficient. It's 0.11, and the associated p-value is 0.06. 0.06 is greater than 0.05, so we would say that the regression coefficient is not statistically significantly different from 0 after controlling for the effects, or while controlling for the effects of other predictor variables in the model. So after, let's assume that we've found statistical significance for our regression coefficients, it's time then to consider the effect size or the practical significance of what we found. In other words, we found that if something's statistically significant, that it appears to exist or it's likely to have existed in the underlying population. The next question should be, how much should we care about it? So in other words, how big of an effect is it? In other words, what is the practical significance? So a logistic regression coefficient itself is not an effect size. If we want an effect size for a specific bivariate relationship that's being tested, we need to look to the odds ratio, which is an effect size. And remember, that's the process of exponentiating regression coefficient itself, because that regression coefficient is actually a log odds. Remember, it's that logit transformation. So if you recall, an effect size is the index of the quantitative relationship between variables, and it's something we can use to compare the effects from different studies that we may have done. So there are many different rules of thumb when it comes to odds ratios, and this really depends in part on the context as well as the variables and the type of model that you're testing. So for instance, if you're looking at option 1, this is going to be most appropriate for a 2x2 contingency table. So for example, you have a dichotomous outcome variable, but you also have a dichotomous predictor variable. Now, in addition, I have two other options here, which I've also seen used in the literature and used by professionals, and this really comes down to you picking whatever is going to be most appropriate. So you'll want to dig deep and then look into, okay, what is the specific context and what makes sense in terms of a small, medium, and large effect if we're going to qualitatively describe the effect size, which again, in the context of logistic regression, is going to be an odds ratio. So you can see that the odds ratio for a small effect is generally about 1.5. Also, we see 1.7. And then when you get to a medium effect, it's going to be between about 2.5 and 3.5, depending on who you talk to. And then for a large effect, here's where we see some differences. It's going to be anywhere between 4.3 to 9.0. So if the odds ratio, importantly, is less than 1, then you can compute the reciprocal to actually interpret it using these rules of thumb. So what that means is that if you do get an odds ratio that is less than 1, take 1 divided by that odds ratio, which is a reciprocal, and that'll put it in the scale of these effect sizes that I'm showing you here. Now, regarding model fit and practical significance, unlike simple and multiple linear regression models, we don't get a true R-squared value for a logistic regression model. Instead, we can use other types of approaches, such as looking at the -2 log likelihoods, the AIC, or more classically and more interpretable is the classification table. And what I mean by a classification table is that we can use this to assess model fit and significance by presenting the percentage of correctly predicted values on the outcome variable. And so how we do this is that if a calculated probability for a case based on the model is equal to or greater than 0.50, then it would be classified as the probability of 1. And everything else would be classified as a 0. And so this way we can try to see, okay, did we, based on the equation, the regression model that we came up with, can we accurately predict people based on this model? So it's a way of understanding how much error our model generates, or in other words, how well our model actually fits the data. So let's look at an example of a classification table you might see from a logistic regression model. And so let's assume this is a simple logistic regression model where we have one predictor variable that is job dissatisfaction, so higher levels of variable mean more job dissatisfaction, and we have a dichotomous outcome variable, which is again going to be voluntary turnover, where 1 equals quit and 0 equals not quit. So those are the two levels or values that one could have for that particular dichotomous outcome variable that is voluntary turnover. So looking at this contingency table, we can see that we have our baseline and our predicted values. So baseline is simply going to be how many people actually, according to the people in our data set that we have sampled, how many people actually left the organization and how many people stayed in the organization. In other words, how many people quit versus how many people did not quit. And so remember, 0 is not quit, and 281 people did not quit, meaning they stayed in the organization for whatever time period we're interested in. And we see 240 people actually quit the organization during this time period. So that means about 53.9% of people stayed and 46.1% of people left the organization. Now, if we look at the predicted, what we can predict based on a regression equation or model that we actually generated based on the data, we can see, well, how accurately can we predict that using the predictor variables? Well, what we'll see here is we have this 2x2 table here. And so we can see that we have, in terms of columns, we have the predicted, so 0 meaning someone stayed, and 1 meaning that someone quit the organization. And we can say, based on this, if you look, we have 202 people that actually stayed in the organization, and that is an accurate estimate. And so that would be 71.9% of the estimates we made were actually correct in terms of classifying people. And so we got that 71.9% by taking 202 divided by 281. Now, if you look to the bottom right of that predicted table, you'll see that we have, this is the number of people, which is 89, who actually left the organization according to our data set, and that we accurately predicted as leaving the organization. And so 89 divided by 240 is 37.1%. So that's 37.1% accuracy there. Not so great. Now, and you see in the off diagonals, these are the errors in prediction we made. So you'll see that in the upper right-hand quadrant, we have 79 people who we predicted would leave the organization based on a regression model, but they actually stayed in the organization, okay? And then we have 151 people who we predicted would stay, but they actually left the organization. Now, if you look all the way to the far bottom right of this table, you can see kind of our overall batting average here, so to speak, which is that we estimated about, or predicted with 55.9% accuracy where people would be classified in terms of staying versus leaving the organization. That's not so great. Ideally, we'd like to see something closer to hopefully 70, 80, 90, 100% would mean that we have a perfectly predictive model, which we're unlikely to get. But we want that number to be higher. Currently, this looks like we can almost flip a coin. There's a 50-50 shot, more or less, and we're only slightly incrementally improving that prediction by including job dissatisfaction as a predictor in the model. So this is one of the reasons, too, why we might go from a simple logistic regression model to predict turnover to a multiple logistic regression model to predict turnover, wherein we include additional predictor variables to explain a different additional variability in that dichotomous outcome variable. And hopefully in doing so, we can increase the percentage of correct predictions that we actually make based on the regression model relative to our baseline data. So in this lecture, we did a quick review of logistic regression. Now, this isn't a very deep review. You can go very deep into logistic regression. There's also other types of regression called probit regression, where you have more than 2 levels of the outcome variable. That's beyond the scope of this particular lecture, but do know that that's out there. But this hopefully gave you a good preview and introduction to what logistic regression actually is, and specifically simple logistic regression and multiple logistic regression. Now, in addition, we covered the statistical assumptions underlying both simple and multiple logistic regression, and we talked about statistical and practical significance in the context of simple and multiple logistic regression. So this wraps up the lecture on logistic regression.